Hello class and welcome to our session. We would continue on amplifiers. We started talking about transistors and its applications. Now in this application we're talking about amplifiers in general, especially audio amplifiers or any signal amplifiers. We did look at a small application earlier, which was a transistor used to amplify the output signal to be transmitted by an antenna. But in this case we're going to talk about audio amplifiers in specific. So amplification, yes, does not need to be only audio frequency, it can even be radio frequency, as in this case. So the word amplifier means it amplifies the amplitude of the signal, but the frequency remains the same. So if your input frequency is 50 Hertz, your output frequency will be 50 Hertz. If your input is 12,000 Hertz, the output will be 12,000 Hertz. But the amplitude of the signal would get amplified or enlarged. So let's look at it in detail. So we talked about transistors. In this case, there is transistor-based amplification plus there is an IC-based amplification. So this transistor-based amplification can either be used in the pre-amplifier stage or in the final stage. In this case, you would see two transistors connected together to be able to work together to work as an amplifier. So such amplifiers are very common, and you would see a larger version of them in bigger push-pull amplifiers, especially used in sound systems and in bigger auditorium-based amplifiers. Let's look at the theory behind it. Yes, as we see in the syllabus, we'll be talking about a few topics: amplifiers, single stage, transistor amplifiers in three different modes: common base, common emitter, and common collector configuration. When you talk about common base, common emitter, and common collector, if you remember, the transistor has three pins: the emitter, base, and collector. And for an input for an amplifier, you need to have 2 pins, and the output of the amplifier needs to have 2 pins. So since we have 3 pins on the transistor, one of those pins would be common between input and output. So if the base is common, it's called common base configuration. If the emitter is common, it's called common emitter configuration. And if its collector is common, it's called common collector configuration. So let's look at it in detail. As we talked about, it could be any sized transistor, could be used in this application. So we look at it in detail. In this case, let's look at an audio amplifier where I have an RC coupled network. In other words, there's a capacitor connected in series and a resistor connected in shunt to the base of the transistor, which is your first stage of amplification. Then your second stage amplification, which goes to your output. When you have a capacitor connected in series, DC is blocked, AC passes through. So this is something you need to remember, and how that's possible, we will study that in detail in the next coming sessions. So looking at the simple amplifier, you have 2 transistors connected together, and a most common way of having 2 such transistors connected in cascade is called a Darlington pair, where you'd have a single IC which will have 2 transistors internally coupled, and you would be able to get amplification. In other words, the gain is multiplied. Example, the gain is stage 1 is gain 1 and the second stage is gain 2. Whatever comes out of stage 1 gets amplified in stage 2, so the gain 2 amplifiers get multiplied, so the gain is pretty high. But the problem when you have high gain is in case you have noise in the input, noise also gets amplified really high. So it's all about the quality of the amplifier and how well you're able to design those stages and couple those stages. In this case, you have a direct coupled amplifier. In a direct coupled amplifier, there is no resistor or capacitor in the series or parallel. And this stage, you would see that I would be able to couple it, and you would be able to see the different configurations, and I'd be able to explain it in detail. So this is, as you saw earlier, you have your emitter as common between your input and output, and as an NPN transistor, you have a PNP transistor and NPN transistor combined, so that your inverted, non-inverted, all your outputs, you'll be able to get the desired output and the gains of the 2 amplifiers combined with an PNP transistor in between. So as I talked about the 3 different configurations, the reason we have 3 different configurations is because having transistors designed by having the doping material, the layer thickness, the voltage required to bias it, everything can be changed in the design of the transistor. And when you study it in different configurations, you notice that there are different ways in which it responds. And those responses are desired when you design certain stages. Example, I want an amplifier which has high output impedance. For example, then you need to use a common base configuration. As you see it here, the highest impedance is available in the output when you have a common base configuration. So designing it for gain, we want the voltage gain to be high, common emitter, very common. then you want to be not that great, less than unity gain, then you have a common collector. You can also have a high gain, especially as talking about high output impedance. You're going to have an impedance matching circuit or a measurement circuit, then you have high output impedance and the gain is high, similar to a common emitter configuration. Current gain is high in common emitter, it's high in common collector and less than unity in common base. So current amplification is not great because your impedance on the output is really high. Power gain is high, moderate and moderate. As you said, moderate. In this case, though it's not as compared to common emitter, it's not that great. Common collector said to have moderately high impedance compared to common emitter. Let's look at it in detail. So next, phase inversion. In other words, when I give a sine wave, a positive and a negative, if the output comes out as negative first and then a positive, it's called inverted phase. Phase inversion happens in your common emitter configuration. That's very common. And to avoid it, when you have two phase inversions, when you have a cascaded connection, you'd be able to get an uninverted phase. So, but in common collector and common base, inversion happens. That does not happen. Input impedance is moderate, about 1 kilo ohm, and the highest about 300 kilo ohms in a common collector. So the input impedance is high, the output impedance is high, and in the common base kind of configuration, your input impedance is low, about 50 ohms. And in terms of output impedance, it's moderate, about 50 kilo ohms. It's very low, about 300 ohms, and the highest of about 1 mega ohm. So having the three different configurations based on the requirement, based on the design, you can have it coupled that way. So we would also study about this in detail where we're talking about impedance matching in a later session. But understand this, when I want moderate impedance, I would consider a common emitter configuration, and I want to match it. I don't want to have any loading effect. Then I talk about impedance to be high, input impedance to be high, or you want output to have high voltage gain but low current. Then I talk about a common base configuration. So this is all about how and why I need a particular configuration to be able to get a desirable output. So we talked about an amplifier, talking about a radio frequency amplifier. In this case, the signal is amplified, and the power cannot be destroyed. Energy can never be created nor be destroyed. That power that is dissipated on this collector side through the circuit is dissipated as a radio frequency in the air. So this is why it was intended to be designed. In other words, energy that is dissipated on your secondary side of your input, on your amplification stage, is what is desired, where you want to dissipate it on higher voltage so that you can reach out a much wider range with a wireless signal. So this is what we normally do with remote control toys, remote control cars and trucks, where we want to control it. So you have a high voltage required to transmit it. On a receiver, you don't need high voltages, you need a low voltage to pick up the signal. You just need to have an antenna to pick up the signal, but to transmit it, you need to have a high voltage to be able to transmit it. Such a simple configuration and common emitter for radio frequency is pretty common for high frequency amplification, as shown with the wireless transmitter. So what should I look in an amplifier? The most important thing when you look at a study an amplifier, example, I'm designing it for an audio frequency. So the maximum gain, the gain is at what frequency, at how much amplitude of gain do I get? So at very low frequencies, I would not be able to get great gains. At very high frequencies, I will not be able to get great gains. But in a frequency between a particular value, I'll be able to have moderate or almost uniform gain. That's a desirable performance. And this band is called a bandwidth. In other words, if I'm talking about an audio amplifier, my lowest frequency might be about 20 hertz, my highest would be about 20,000 hertz. This is what I desire to have in an audio amplifier. I should be able to do the low frequencies of audible hearing, at the same time higher frequencies for audible hearing. Any other frequency that it amplifies would not be suitable for me because I'm not able to hear it at the end of the day. So designing amplifiers to be able to do a specific task of amplifying a certain range. For example, I'm designing an amplifier to amplify a signal to be transmitted wirelessly, and it's in the radio frequency range. I need to pick one that works on that particular frequency and efficiently in that frequency. The efficiency of that particular frequency also matters. I could have a transmitter that's working on a particular band, and if I have to change the frequency and the transistor does not support or give me high gains in that particular frequency, my efficiency won't be that great. So understanding frequency and identifying at what frequency to what frequency is the gain, the moderate or above the desirable value, that is a frequency band I need to consider as my bandwidth. So the word bandwidth would be coming up very often. And in talking about the gain of an amplifier, use the word decibel, dB. And that's something that you would come up quite often when you're studying about the details of amplifiers and talking about the calculations behind them. You would see that in the upcoming sessions. So let's go back to the syllabus and review our understanding. So transistor, a 3-pin device, can work as a switch that we talked about in common emitter configuration. And we talked about transistor as an amplifier. I could work on a single stage, which is one transistor working as an amplifier, or I can cascade them. I'm talking about common emitter configuration. If I cascade them twice, the output is inverted twice, I'll be able to get uninverted output as in my output stage. We talked about the 3 different configurations: common base, common emitter, and common collector, where the different configurations have different benefits. The most common emitter is moderate on everything, has high gains on voltage and current, but common emitter and common collector have their own benefits, where higher input impedance or higher output impedance. We talked about RC coupled, where you have a resistor and capacitor circuit in series and parallel with your capacitor in series and a resistor in parallel with your input. This would be an application when you're talking about AC filtering. AC passes through and DC is being filtered out. You're talking about AC, mostly amplifiers. We're not talking about DC. It's mostly AC. So those are the ones that we talk about, RC coupled amplifiers. We also saw an application where we talk about direct coupled, when you saw 3 transistors connected in cascade, and the gain was direct coupled. There was no capacitors in series. And the next would be the frequency response. We're talking about the frequency response. At what frequency will the amplifier be able to give me desirable gain or desirable amplification in reference to dB? And we talked about the wide range of audio between 20 and 20,000 hertz. And for radio frequencies, for the particular frequency I'm going to operate at, the resonant frequency of the oscillator and the antenna working on that particular frequency to dissipate the maximum power, so that I can have the maximum range of transmission. So let's look at this in detail as we look at specific applications with a transistor-based amplification in the next session or two. So I'd like to go back and show you a little more practical aspects with a video presentation. These days, you don't use transistor-based amplifiers with transistors visible on your board. In this case, you have a transistor-based amplifier, but the transistors are embedded into an integrated circuit. So you would get the integrated circuit. It's a very common Class D amplifier. We'll talk about the classes later, where all your transistors, the whole circuit, when talking about the word IC or integrated circuit, it's a complete transistor-based design amplifier built onto a single chip, on a single IC, encapsulated, and you'd be able to use it as an amplifier to drive a decent speaker right with such a small board. So amplifiers are not big. The word amplifier is to amplify the signal, but their size does not have to be big. So I can use even a single transistor as an amplifier. I can couple them 2 together. I can use them as an amplifier. I could have an IC developed based on transistor-based amplifiers integrated into a single IC. So this is what you would see amplifiers as in the smaller form factor. When you're talking about bigger form factors, yes, you would have transformer-based, center-tapped, coupled, NPN, PNP combined together to be able to work on the entire spectrum band and amplification. And those we would see with practical demonstrations as well as in the upcoming sessions. We're talking about the amplifiers in detail. If any questions, please reach out to the classroom and drop in a message. And you can also drop me an email or reach me on WhatsApp for any questions or concerns, and I will cover them in the upcoming sessions. Thank you and have a great day.